some other distribution also we will be seeing, and curve fitting is the last thing we will be seeing here. So okay, so I'll be using Jamboard and pen here for this. So just couple of things we will be starting with. So to start with basic, we will be starting statistics. I guess it's visible. So statistics, we that is a very important tool that we need in all aspects of science and other non-science as well. And any kind of data analysis we are trying to do, we need statistical significance. We keep talking about p-value. So the basic statistics that is very important for all of the things we perform to do. Now statistics can be two things. One is descriptive, another one is inferential, right? Now in descriptive statistics we have very basic stuff that we try to learn, that is mean, median, mode. You all are aware of these things, right? So mean is, I'll just quickly say, mean is the average, basic, like average of different values. If you have 0 1 say 3, average will be 4 by 3 or something. Median is like if you divide it by 2 and then uh, the middle value, and sort of mode is what is mostly coming in the data set, right? So these are the mean, median, mode. That is one of the descriptive statistics. Followed by another thing that we have here is so mean we usually represent by mu in the statistics. So that is one thing, and then followed by another thing we have is here is range for the data. What is the range of the data? And then we have standard deviation. Okay, so how the data is distributed across all the things. We have seen his histogram yesterday. So there might be a data which looks like this. There might be a data which looks like normal distribution, similar kind of distribution, but more distributed. So what is the standard deviation? That is also we will be seeing. And then we have so that these are all coming under the measure of dispersion, right? So this is the basic stuff that I am assuming all of you are aware of. So this is the descriptive statistics we have. Now moving forward to inferential statistics. Just a second. That we will be mostly talking today is the inferential statistics. The very first thing that comes here is called a random variable. Anything that we designed as x. What is a random variable? That a function that maps to any random process. So we can call it a function that maps to any random process. What is a random process? Everyone knows the example. you know, uh, Toss a coin, right? Toss a coin. So if you toss a coin, say we have x, what could be the values possible? Say 1 if there is a head, or 0 if there is a tail, kind of that thing we have with us. So this is basic, is a random variable. Also it could be, say if I ask something, what is the amount of, say we had cyclone a few days back, so amount of rain uh, for cyclone or something that, right? So these are the certain things that we can calculate. So whatever is, these are the random phenomena. So whatever values we are assigning to it is called a random variable. So here random variable is x, just calling x, right? Just calling x. Audible, right? Yeah. Huh? Okay. Now, okay. Thank you. So so that's why we, so now random variable can be of two types. So we are talking about this kind of random variable where we have discrete values, that is called discrete random variable. And if something that could be anything, like tomorrow there could be 1 centimeter rain, could be 1.1 centimeter rain, I don't know, right? So amount of rain that we, so if we are trying to predict the amount of rain for say tomorrow or any day, it could be 0 centimeter also, anything. So that kind of data is called continuous random variable, right? So these are the different random variables that we can have. Now these are the thing that is depends on the your probability. So that there comes the probability. Just add another frame. Okay. So if I tell you that I have a fair dice, and if I have to roll these dice, then what could be the probability of each side, right? This is your discrete uh, probability. So all things should be 1 by 6. Your probability of getting 1, probability of getting 2, probability 3, 4, 5, 6, all should be your, say, 1 by 6, right? All are in the similar, if it is a fair dice we are rolling. So this is again discrete probability. So so your x will be 1 by 6. For so x of 1 will be 1 by 6, x of 2 will be 1 by 6. So whatever we are getting is 1 by 6 of all those things, right? Now if we have a biased die or something, biased dice, then this may not be the same thing. So there might have something is 1 by 6, something is 2 by 6, something is nothing, 3 is probably never coming out or something, then 4, 4, 5, 6 or something like that. So this is biased dice. So then probability won't be equal, probability will be different. Still that is a difference and discrete probability, right? Discrete variable. So these random variables are discrete random variable. And if I have already given you an example of rain. So if I say, if what is the x, so to get that, so these are discrete probability. If you see any continuous probability, so this is the amount distribution, we have seen histogram. So this is the, say, distribution of the amount of rain. So we have, say, frequency, and then there you have amount of rain, right? So there is, say, 1 centimeter rain, 2 centimeter rain, 3 centimeter rain, and we can ask for a particular area. Okay, what is the probability that the rain will be happening between, say, 2 centimeter to 1 centimeter. So this is how you define a continuous probability. Or you can give even strict cutoff like zero point 0.5 to zero point 0.3 or something, kind of that thing. Or even you can ask what will be the probability if that is the 1 centimeter rain is happening. But the variable, random variable x for this case could be continuous, right? So that is called a continuous variable. Now you have a so this random variable x has a two things that I already discussed. One is discrete, that we have seen. One is continuous. Right. Now let's coming to the so this kind of distribution what we are seeing here are called binomial distribution, because it's so I just yes. So let's start with the first distribution, that is called binomial distribution. So let's say we have a like our main x, how we are defining it. It is the number of heads for 5 flips of a coin. So what could be the 5 things that you can get, for this thing? So x could be either 5 heads. Okay. So what is the possibility of this? Or could be 5 tails or something. So this will be, or it can be 5 tails also. So for here we have, so probability of this is, so let's take the probability. Probability is x equals to 0 because we don't have any heads here. So what is this? This is 1 by 2. That is the each time we are having. So probability of each time is 1 by 2, and that you are doing for 5 times. So this is the probability of happening this. So this will be 1 by 32 times. That is the possibility of this event. Similarly, this event also you can get only once time, right? So x equals to 5 head. That will be also can happen once time. So 1 by 32 will be the probability of this. Now, if I ask you what will be the probability of at least one head, at least one head could be then say t head. Also, this can happen as t head tail. Can be t head tail, and so on. So this can happen as 5 times, right? So your probability of x equals to 1 will be probability of x 1 by 5 by 32 times, right? This is the 5 out of 32 times. Similarly, you have a distribution. So x equals to 2 will be your probably 10 by 32 times. That is 5 by 16 times. So if you plot all these things up to x equals to 5, you will be seeing a graph. So say this is this should go like this. So 1 by 32, 2 by 32, 3 by 30, 5 by, so 1 by 32, 5 by 32, 10 by 32, and then I guess it will come as 5 by 32 itself again. X equals to 3 will be also kind of 5 by 6, and then 5 by 32, and then 1 by your 32. So this distribution itself is called the binomial distribution that we are getting out of this, right? So how we can formulate this? We can formulate this nice way. So we can formulate it is like given it here also, like this, right? So this formula is given here. So that's how you can formulate a binomial distribution, right? I'm not writing it here, there again. So this is the binomial distribution. So we will now see how we can do it using here in the notebook. So I'll ask you to open the notebook, and then before doing that, we will do couple of quick things, and then binomial, and then come back to other you know uh, things. To start with, you can import all these packages. I'll just paste it on the chat. So uh, once you open these things, I, I'll just tell these things. So so the first thing, just a couple of things before we jump into the binomial distribution. So can we plot as just simple function here that 2x plus 3 or 2x minus 3 in the same graph in a domain of 10 minus 10 to 10. So we imported numpy. So we will be taking care of using numpy. So we are creating two variables, y equals to 1 equals to 2x plus 3, y2 equals to 2x minus 3. And if you are plotting x, y, and this star are for red color and blue color. Okay, so you can see we plotted two line, that is 2x plus 3 and 2x minus 3 here, right? So uh, this is red one with star and then blue one with dot. So yesterday I showed about that or the I guess first class we showed that NumPy has those sine and cos. So can you just plot a function for sine and cos, seeing the same function within the 3 pi 2, minus 3 pi 2 positive 3 pi. You can use SciPy also. You can use NumPy. And it will be in the same fashion. You just have to import that package, call the sine and cos, and you can just simply plot. So if anyone you are doing this, once you're done, can you just paste the code here, or just let me know if there is any issue you are facing. So here we have generated a random number, right? So we have seen the random numbers here. Hello. Okay. So we have random numbers. We have seen the random numbers. It's coming from expectations. We have expectation, number of occurrence, and probability. And we have discussed about this x as a random number. So we will be seeing how we can generate, random number in the Python, right? So for that we have a function called random. So you can generate, if you do random dot rand int, so rand int will generate random number between 0 to 10. So one number between 0 to 10 it will generate. So 1, if I rerun it, it should give some other number. 6, if I rerun it, it will give 3. So you can rerun it and it will give you a random number. If you want a, if you want a float that is between 0 and 1, including 0 and 1, you can use random. Okay, so this gives you some random number. So if you rerun it, so that will be coming between 0 and 1, including both 0 and 1. Now it's audible. Okay. I guess I was mute sometime back. Okay, so to randomly choose from a choice given, so you can also ask that if you have a set of data, you can ask to choose the random function, right? So you have a 0 1 2 3 5, you can just ask it to choose, so it will choose multiple things multiple times. So it choose 0 1 3 5. So these are the three things that for basic things that we can do. So now your job is to write a program that generate 50 random integer between 3 and 6. That could be 3 6 multiple times, but you have to generate between 3 and 6 but 50 times. Can you generate and put it in a list or something? So if you any one of you are doing this, can you just paste the code on the chat or anything? It will be helpful for others also. Otherwise, I will just show you. You can use this random integer in the rand, and if anyone is like doing, just paste the code. uh, Anyone, or just any code snippet or anything, any fragment of you are doing this, or are you able to install random? Or you can just do with me maybe. So I hope the screen is visible. So what you can do, say, let's assume we have a empty list or something where we want to, add the thing, and then for I in range, say we want to make 50. So you can create x dot append random dot rand int random dot randint. Then what will be in the bracket? Anyone? Just you can type in the chat or unmute and tell me. So it also showing you here. Anyone, anything? What will be in the bracket? So you can put 3 and 6, and then let's see what is. You can see X. So we have a list that consisting value of including 3 and 6, 50 random values. So these are randomly generated. So why it is very important, like we need to see how a randomly occurring event can get you what all the different values, right? So that's why we have random variable, and very fast distribution that we are going to see is binomial distribution. I've shown you how it comes from the random variable in any random event. So random event can be a discrete event or can be a continuous event, but it depends on probability. So p of x equals to k is equals to that, the formula is given here, that we have also seen here. So we are going to plot these things using, so we are doing to fair coin flip, and we will be using so the answer we will be using binomial. So this is binomial here, binomial distribution. So it's giving you all the details here. So you can see you have you have n is the number of occurrence that you want, p is the probability, and what is the size you want, okay? What, how many trials you data set size you want, and then you can plot that in and you can change also the bins. So these are the pandas thing that you have already seen in the histogram. So taking this 1000 size, what is the distribution plotted is looks like this is the binomial distribution. So this is similar kind of this distribution what we have seen, and also similar kind of distribution what we are expecting here. So this has to go like this, right? You can also use a displot. Yes, so this is another thing that we have disport in SNS. That also will that's also like we you can change the bin size, but this is also giving you the same plot in another fashion, right? So this is the binomial distribution that we are seeing here. So I'll just paste this code with you. You can just try this here. So you have any doubt regarding binomial distribution or random variable per se? Any of you getting this plot? Anyone, if you got the plots? Okay, so if you're getting this, let's have a couple of other background things like. So all of this distribution, like including the binomial, actually come from a basic distribution called Bernoulli's distribution. Okay, I'll try to fit it using different problems. So what is Bernoulli distribution? That asks what is the outcome of a single Bernoulli trial. What is a Bernoulli trial and what could be the thing? Say, if I ask you one simple question, if I toss a coin, what is the chance that it comes up head? Or you can have, so this is the very basic example. I just try to give some simple but little bit off example. That is, if I pick up any random, so this is random variable, right? So everything has to be very random. So any random, Indian, what is the probability that he or she is a heart surgeon? So what you get out of this, both questions could be answers using either 0 or 1, or yes no, or a sort of binary answer, right? So this is, so what is the chance of its head, so whether it's head or not, whether it's a heart surgeon or not, right? So you can answer it within using simple 0 and 1. That is very basics of your random variable distribution, right? So that distribution will look like 0 and 1, then some values here, some values here, or something like that. So that is probability. That probability is called by Bernoulli distribution. Now there are certain probabilities including binomial distribution. These distributions are based on or derived from Bernoulli distribution. Let's split them into, as of now, three things, easy things. Very fast that we talk about is binomial distribution, right? Binomial distribution. There are other distributions also, like negative binomial distribution, that we'll be also talking about. Also there are geometric distribution. Okay, let's try to pose some question and then try to understand these distributions. Number one, binomial distribution. If I ask you, I have a coin, I tossed 20 times. I have a coin tossed 20 times, right? What is the probability of getting head? Probability of getting head 14 times. Is my handwriting visible, or are you able to see? Or shall I zoom a bit? Can anyone let me know if this is better? Are you able to get my handwriting? Are you just, or is that okay? Or I can change maybe. Yes, good. Okay. Okay. Thank you. So coin toss. Okay, I just select this. Okay. So so this is said, this is the question we are trying to pose here. What is constant here is 14 times. We are focusing on 14 times out of 20 times. 20 can be very, but how many times we want the head, we can, accordingly we can put it. So that's the your question. So even if you remember, when I start in the earlier slide, we are telling you that, okay, what, how many times we are getting head. It's one time, it's two times, it's three times. That's why x equals to 1 2 3 pops up, right? All this x equals to 0, x equals to 1, x equals to 2 3 4 5, all are coming from the fact that how many times you want to see the head out of the your all distribution. So that's how this our binomial distribution is coming. If we are talking about negative binomial, what could be the question be? Question could be, what is the probability of getting a third head by eighth toss? Right. So here you have to focus on two things. I'm telling eight toss, but what is, I want to get also third head by that time, right? So this is the difference between these two things. Here I want, okay, we have 14 times, but here we have another restriction that by 8 time can we get a 14 or not. So this is another thing. Now try to pose a question for geometric distribution. So if I tossed one coin, okay, what is the probability of getting tail or head after, say, 8 toss? So what is the probability we are getting after 8 toss? So the ninth toss will be your tail or head. So that is the distribution you are going to get, is called the geometric distribution. So these are the examples. Let's see what are the basically definition of what is happening here. So in the first case, when I'm talking about tosses coin 20 times and what is the probability of getting head at 14 times, we are trying to distribution of success in the, so we are trying to see the distribution of number of success. So we are asking how many times it's getting head. When we are focusing on negative binomial, we are trying to address how many trials I need to achieve my goal. So my goal here is getting third head. My goal here is getting third head. So I'm asking question whether by eighth attempt will I get my goal or not. So that is your negative binomial, right? And then geometric distribution is going to number of trial to get the required success. So number of trials to get. So this is a extension of number of trials. So here we are asking question that whether we are going to get, whether we are going to get third head by that time, and then here we are asking whether we are going to get a tail after 8 toss or not. So this is the geometric distribution that we have. So we have these three kind of distribution that is again, derived from your binomial, Bernoulli's distribution. Then move forward to, Then move forward to another thing that is very important here is Poisson's distribution. Okay, so before coming to Poisson distribution, just let's try a couple of thing on notebook. So I assume you have done these things. This I can also paste on the chat, but yeah. So you can try that also, as well as let's move to another thing that is called probability mass function. It is the probability. As of now, we were talking about distribution. This is probability. So this is using binomial and finding what is the probability of this getting these things. Okay, so this is of k equal to 5 will give you 5 success in the 10 flips, and each with a probability of zero point 0.5. So this is a toss happening. So zero point 0.5 is the probability of each event. You are doing 10 flips of the coin, and for the 5 success what you need. So this is the probability, right? And you can do it for multiple probabilities. So if you have probabilities zero point 0.5, if you don't have, if it is some sort of bias, you can use zero point 0.3, zero point 0.8 also, and see how the distribution actually varies. So you can see the zero point 0.5 is here in middle, zero point 0.3 here, zero point 0.8 here. So the peak is here basically, and the peak is here. Highest peak is at zero point 0.5, highest peak is at 0.6. So this all are your binomial distribution. So what I will suggest you to do, for next couple of minutes, I will paste you this code in your chat. You can quickly try with other stuff also. So I have shown you here, point 0.5, point 0.3, point 0.8, but you can move forward and check, okay, what is happening at 1, what if it's happening at say point 6 or 7, something else, and plot that and check maybe. So that will give you another understanding of how binomial distribution is happening. So okay, any of you got these things? So let's move forward. Let's see. So you can, given the equation we had here, binomial distribution, right? So you can form this. So using this equation, you can form yes, form this value also, rather than just calling the function and get the plot. Also, we have defined another for cumulative density function. So cumulative density function is basically summing all the values, will give you a cumulative density function. So we'll run this and then plot these things on a so this is a data frame. So let's just print this and you can then see it. Yeah. So we have all these numbers. We are just trying to plot it with both of the things. I'll just on the subplot. So what we are trying here, we are trying to use both of the probability measure functions. So one is defined, that is defined here using PDF of the package stats binomial, and then we are using the own formula, our own formula that we had, right? Just a second. Uh, Sorry. You can use both of these things and check. So we are going to see that how they are going to define. So the actual function they have. So this is two different things that we plotted here in the different plots, and you can see both are the same things. So either way, you can use the package in the Python, or if you want to write the code from scratch, you can write, and it will giving you the same results, right? So I will copy paste also this in the chat. You can just try that also on your own. So you can try that on your own. Anyone who has issue with following this up, like, I'm pasting the codes, but if you want me to stop, I can show you the code, and then we can spend some time here also. So you can also check the cumulative density function of both of the cases. We have CDF function here. We have CDF function, and we have inbuilt CDF function, and what we defined for both of the cases, you can see the values, probability values are coming exactly same, right? So you can write their own CDF function and try that. So if I plot this also, you are not seeing any difference. Both are overlapped. I can do that using subplot. Just let me just try this subplot. You can see. The cumulative is basically summing it up, so you will see upward thing, and both of the cases you are seeing, it's the same curve. So it's either or, you can define using your concept, or you can write using, you can just pick up stats and then binomial distribution, that should also work.
Yeah.
So I will just give you this plotting info. Plotting is similar like the earlier one we did for PDF. Probability density function. This is cumulative density function is also uh, same, right? So this one and this curves are same, and also we are getting the similar values. Anyone, if you are getting the similar value? Anyone getting this plot, or if you are not getting, you can ask me. We can just check the codes, or if you're getting any error kind of thing. Okay. If not, let's move forward with another quick thing that we have to discuss. That is Poisson distribution. So in Poisson distribution, an interesting factor called time comes, right? So in other stuff, we have seen the numbers, how many times, how many things are coming, but here we have another third factor called time. So let me pose a problem for our random variable. So we can say number of cars passing through main road in last 1 hour, right? So this is your, and definitely your expectation E of x will be your n of p. So number of occurrence and then probability, right? And let's pick it as a lambda. Simple, just assume this as a lambda. So you have lambda cars per hour. That is your, so expectation is the number which is basically multiplication of how many time it is occurring, and the probability, right? And if you change this to minutes, so number of 60 car per minute. Right. And Poisson distribution is basically showed as a p x equals to some probability for k. It has to be lambda to the power k by k factorial. I'm not going into details of this derivation, but this is the distribution. So this is your distribution, Poisson's distribution, and we are trying to implement this on Python, and let's see how we are getting the distribution, right? So Poisson distribution is a discrete probability distribution that represents the probability of number of events that can happen in a fixed range of time. So time is the very essential factor for determining your Poisson distribution. and it can be say applied to model number of cases hospital can have in an hour, or cars passing through this in an hour, kind of that thing. So that is your Poisson distribution. So what you have to give is mu or this lambda. That is the only thing that you have to give here. And how many, what is the size of the data you want, and then you just give stats field distribution of the Poisson. So Poisson distribution you can see here, it is essentially or similar kind of thing that it is giving you. Yes, I guess you can also add bins here. Bins equals to say some 20 or something, I'm not sure. Yeah, you are getting 20 bins. Let's reduce to some 10 bins. Yeah, some sort of distribution, or if you are doing KDE true, you can see there's a discrete, but we can fit it to get the KD. So you are getting something like this. So this is discrete. We are trying to fit continuous. This is not a good way to do this, but okay. Yeah, you can just for the checking purpose we are doing this, right? Otherwise this is following the main trend of Poisson distribution. I'll paste this also in the chat. And then the same probability distribution function for these things. So probability distribution function, now you can see how is the main distribution functions looks like, right? So this is the distribution, and then you can get all the stats of what is the success per event of 3, or event of 4, what is the sub. So you can see those stuffs. So this is basics of Poisson distribution, what I have shared with you. I will share this code as well. So I'll give you some time to just at least do this Poisson distribution, and then quickly we will move forward to normal distribution, and I guess just a couple of other things quickly. Anyone any facing any issue regarding doing this or something? You can keep KDS false also. That will give you proper distribution. Okay, so let's move forward. Next thing that we are going to see here is on central limit theorem, and then that will move forward to your normal distribution, right? So what central limit theorem is saying, that if you have a set of random numbers, okay, they are tends like to have a more, distributed. So if it is range between say 0 and 100, that they are tend to have more number of things towards mean. So whatever your mean is here, right? So you will be had more occurrences during towards your mean. So that is your central limit theorem essentially is saying. And then that is extended to normal distribution. And what how the normal distribution is actually, it has a complicated formula, but essentially if you have a population, say this is your whole population, you never actually sample using population, you just sample a small part of it, and that is called say sample population. And if you take that thing and then take a mean of it, and multiple times you are sampling across multiple things, and then taking mean of that, right? So you will be have mu1 mu2 up to say, if you are doing this for n times, you have mu n. If you plot a distribution of them, what that will give you is called a normal distribution. So in exact, what is called sample distribution of sample mean, so is normal distribution. When you sampled n equals to infinity times, or very higher number, you can say, right? So sample distribution of sample mean, so these are your, sorry, so these are your sample mean. So sample population, not population mean, it's your sample population. Sample population, the mean it gives is called sample mean. And sample mean the distribution, and if you take the sample out of it again and plot a distribution, that will be calling your normal distribution. If you are taking, n number of samples out of this population, and then and then taking the mean and then check the distribution. So let's see just the part of it. So what we are doing here, so we generated, so matplotlib we have seen yesterday, so I will just cut that and paste it here maybe. So matplotlib is the packaging side. So otherwise, if you have taken, yes, so otherwise, so random seed we use usually to fix the random number, like every time, because if you run random things, it will be coming different things different time. So we are generating 1,000 numbers, you can generate 10,000 numbers. As long as many as number you will generate, you will get more normal distribution. So you will be having outside the gate. So so np random normal distribution, so we have 1,000 numbers we are generating, and then we are plotting them, right? So if you plot them, you will be seeing, see, uh, normally normal distribution. And if I plot again, you will see another normal distribution. If I plot it again, so this distribution are changing, right? If you are using say 100 times, then it's not that normal, but you can say it's sort of normal. If I use say 10, not very normal, right? So and more the number you will be increasing, say if I do 10,000, it will be better than 1,000 even. It's getting proper normal distribution, right? So if you given increase 1 0, I don't know that is doable. Yes, doable, and you are getting even more, good number of things. So the another thing I would like you to try maybe later, that just I will paste it. You can just continue doing that. That just plot, 10, 100,000, 10,000, 1 lakh, 10 lakh, and see how the distribution is improving. So more you does that, more you do that, you will be able to see that it is getting a proper normal distribution, right? So so that is the thing about normal distribution. And see this is the standard normal distribution what we just got here. So essentially this is the formula, and similarly you can get this using stat.norm, right? See, you are getting. So we have 1,000. If you want to increase it to 10,000, even better normal distribution, let's go to 1 lakh also. You can get even, I guess, very nice normal distribution. See, so this is essentially the thing we are doing here, and that is using basic histogram plot. Here we are using stats norm. Again, normal distribution, we are asking Python to give you a normal distributed data, but here we just use the theory to see if we have a random number of huge scale getting more and more and more, you are tend to get more normal distributed data. And similarly we have probability density function, that is actually very normal, normal distribution thing. So yeah, that's the thing that we have here. And so I'll just paste the code here. So this is for plotting normal distribution, and then it's probability distribution function code. So you can use this quickly and check. Another thing that we have, I'll just quickly say. So this is again, we are using, the function as given the given this formula. Using this formula, we are just writing this formula in words, and then just trying to do that. What is the error it was throwing is normal. Okay, sorry. Okay, so I will just create a subplot to show both of them side by side. I'll just copy from the above. So plot dot subplot. So you can write your own function and plot them to see how you are getting. So similar, right? So again, we are trying the same thing. So we wrote our own function, and we wrote the probability density function for the normal distribution, and we plotted it. You can do this. I pasted the code in the chat, and similar way it will give you the things. Let's not go here, as I'm almost on the end. You can color like this on the base of how many standard deviation you want. So this is the standard deviation. So normal distribution is basically you get the whole data within 3 standard deviation, right? So very important thing is, your distribution is, so 66% of your data approximately comes with between your 1 standard deviation. So mean plus 1 standard deviation and mean minus 1 standard deviation. So it's, so 66% data will come within your mean plus minus 1 standard deviation. Mean plus minus 2 standard deviation, your 91% data will come, and all your 99% data will come in three standard deviation of the data, mean plus minus three standard. So three standard deviation, after three standard deviation you will be only left with very less number of data, right? So that is beauty of this standard deviation and normal distribution. So that also you can do. I will share these things codes, and you can also try these things. And then you have your cumulative distribution functions for the same also. So since the both I plot together, and it's overlapping cumulative density function. Now another quick thing that we can do is uniform distribution, called uniform distribution. Uniform distribution is something that, say you have some value, say x or something, and then as of now saying we have some plots like this, okay, and within a range only the value will be working, right? So we will be having a value here, not only any of this range. So if probability of x is say greater than zero point 0.5, you will be or just let's write in some other sense. So x of x or something k, I will write greater than zero point 0.5. Then only you will be getting some value, say 1 or something. So here x equals to this one value line. And if it is less than 0 or anything else or greater than, or we can define a particular range, say k is between your say zero point 0.6 and zero point 0.5, right? And if it is like less than zero point 0.5 or greater than zero point 0.6, the value will be 0. So that is your uniform distribution that we have. So these all values are 0, and here you will be having only this one value. So that is called your uniform distribution. So that is called uniform distribution, right? And then you have again stat uniform to do that. So you have to give two values b and a, and then you can get a uniform distribution. So usually everything is uniform, but if you increase the data size, you will be seeing again, everything is very uniform, right? So all are the uniform. And similarly you have what you call probability distribution function. So you can see there is nothing in between. So we choose 0 between 0 and 5. So between 0 and 5 everything is your high, and then it's going down, probability is going down to 0, right? And similarly you can plot the probability distribution function and CDF function. We just show the values here that is there. I'm not going deep into this. Maybe I will wait for a couple of minutes for you to just go through this. I will just paste the code for uniform distribution also. And I guess I gave you normal distribution. So this is normal distribution with standard deviation thing. Or also you can try. Wait for a couple of minutes, and then a small part that we can do is plot fitting the distribution. Given any distribution, how can we fit to any of these different distributions that we have here? So the last part here, we are going to create a random variable. So we are generating is using binomial as of now. So you can generate using, let's start with 10,000. So we are keeping random state because it will generate the same thing, right? And then you can ask it to fit. So norm fit will fit the data into the normal distribution, right? So we have binomial fit, we have again normal fit. So the data we fitted into both of the things. So binomial fit we are showing in the red, and normal fit we are showing in the blue, right? So given a data, how we are fitting it here is one thing. We can also do, what are the stats for that. So this is the average and this is your standard deviation. So average is 4, standard deviation is 1.5. That is the data. You can generate any other data randomly and then try that. So we had generated that in the very beginning. We can just copy and do that maybe. So let's use this also. We can try and use this. So uh, we have to convert it to NP array. You have to give it as NP array, and then you can also run this. See, so with random 50 numbers, we are seeing very odd patterns across all these things. We can increase it to say 100 or something, and then let's see. This should get better. I don't know, maybe a slightly. Then to 1000 slightly, because we have only few numbers. That probably causing the problems. If I give you to 0 to say 100, it should do a little better also. No, not really. Okay, so maybe 0 to 50. So here what is doing good is your normal fit. No, red is doing good. So binomial fit is doing good, and then normal distribution is not doing good. We can maybe try another, because these are all random. So not really doing well. So we can try something very in small range maybe. So say 100 or something. Yeah. So all these kind of plots are basically how you are fitting that data. So you can see we can use the data to fit into a normal distribution. We can use the data to fit in a binomial distribution. So that is very important to understand the dynamics of your system, so that you know when to use which distribution, so that you can fit your data into that distribution. Right, so I will just paste again these three comments in the chat, and yeah, you can just quickly try that also. Curve fitting is very important when you are doing some mathematical modeling, where you know how your system behave and you have some data with you. You can try to fit those data into certain this distributions, and explain your system's dynamics. So with that we will like covered very quickly due to like we had constant time constant. We just covered the plotting basic equations. You can do sine equation, cos equation, and also by default some you can use default settings for all of the things. We check the default codes that packages comes with packages. Also we tried our own methods using the basic formulas we had, and we try to compare on multiple scales that how that are useful for both cases. We have seen binomial distribution, we have seen normal distribution, we have seen uniform distribution and Poisson distribution, and couple of other basic stuffs on your distributions, basic statistics. And then moving forward to fitting a curve, giving given a data, how you can fit it to normal distribution or any other distribution. You can try this with other distributions like uniform distribution kind of thing, but it depends on the data again, how good is the data and how you're trying to fit it to the whatever distribution you're trying to fit it. Okay, so I shared the feedback form. You can give the feedbacks. It is very useful for me at least. Uh, if you try these things, and I will be here for a couple of other minutes. But if you are done, you can leave also. If you have any issue, anything, any plot that you want me to retry, explain you again, I can just do that. So I just ran through a lot of things today. Probably, what I will do is I will upload this all in the GitHub and share the link with you. That's I guess will work better, so that you can just go and try all the things on your own. Uh, yes, sir. Yes, you can get all the thing in one file. So I will give you all the links by the end of this week. I will upload it in some place or GitHub or Google Drive, and can give you the link. Right. So it's with me. Or can I share here or upload any file here? I don't think so. Or at least just let me download this as of now and upload it the GitHub and get you the things. Just give me a minute. At least 2 days thing I can upload quickly. Okay. Can you just check if this is working? So I uploaded today's code in the GitHub. I can upload other things quickly, and I can share the link with you, so that you can also share with the students. Okay, if there is no more question, we can conclude. And tomorrow, Roshan will start with linear algebra. Uh, Tomorrow. Okay, I'll just confirm that what's we are doing tomorrow. Okay, have a good day. Thank you all. Thank you. Thank you for joining.